Hey everyone, and in chapter 15 we're going to talk about two related concepts, which is reaction rate and chemical equilibrium. Reaction rate is a concept about how fast a reaction progresses. In other words, how much time or little time it takes for the reactants to convert to the product. So if you're looking at these two reactions, for example, right, here's a reaction where a red and blue compound is combined to form a green one, and this one we have a purple and yellow forming a gray one. We can see that the reaction on the left is making more and more products, and by this time period all we see are products, whereas with the reaction on the right we still see some reactants even beyond that third time period. And so that tells you that the reaction on the left is a lot faster than the reaction on the right, because all the reactants have been converted to the products at an earlier time point. Now, the reason why a reaction goes fast or slow really depends on the specific molecular changes that occurs when the reactants become product. And the more molecular changes have to take place, then the slower the reaction is. And this is really something that you will talk a lot more about in the second semester of general chemistry. One point to make is just about how, what actually determines the speed of a reaction. Well, there's really three different things that controls how fast the reaction proceeds, and those three factors determine how often collisions occur between reactants. And this idea that collisions is what eventually lead the reactants to become product is called the collision theory. And so what are the factors that control collisions? Well, the first is just the number of reactants. If you have more reactants, in other words, the concentration of the reactants is pretty high, then there are higher chances of them to randomly hit one another, and then they have the opportunity to react to make chemical bonds or to break some chemical bonds. Okay, so that's the first thing, is concentration. The second thing, it turns out, is that there is a factor called the activation energy, which is sort of a barrier that the reactants that collide with each other must overcome. So imagine you are jumping over a bar that's placed, let's say, at the height of your knee. Well, it's not going to be that easy to jump over that barrier, but if you're pretty fit, you might be able to go over that barrier. Now imagine that that bar is now raised so that it's the height of your waist. Now it becomes a lot more difficult to jump over that same bar. So that's really what activation energy is the height of that bar. Different reactions have different values of activation energy. So the higher the bar, the higher the activation energy, the harder it is for the collisions to actually make products immediately, and as a result, the slower the reaction. So in this two cases here, all things being equal, we would expect the reaction on the right to have a higher activation energy than the reaction on the left. The last point is about the orientation of the reactants. So the way reactants make new bonds and break old bonds is they have to be on the same orientation. So think about two people coming together to shake hands. They have to be facing one another for them to be able to shake hands with each other. If one person is facing the opposite way, then that handshake will not take place. So that's the same idea about the orientation of the reactants, is the reactants have to be facing each other in a certain way for those bonds to be made. And so, if that doesn't happen, then you're not going to get products. So a couple of things to summarize this reaction rate point is that we typically get a faster rate with increasing reactant concentration. Temperature is a factor. Temperature, it turns out, causes molecules to jump over that activation energy a lot more easily. It's not like the bar is lower, but then the molecules have more energy, so they can jump a lot more easily. Think about if you have a bar at the height of your knee, but then you're trying to jump over that before you have lunch and after you have lunch. You're going to have a lot more energy after you have lunch. So that's really what temperature is doing, is giving the molecules more energy versus less energy, depending on whether the temperature is high or low. slow. And those are the two factors that would govern how fast these reactions go. So we want to continue our discussion of chapter 15 with this concept of chemical equilibrium. This is about certain reactions that are different than the types that we've been talking about so far. So a lot of the reactions we talk about, like combustion reactions, for example, are what we call irreversible reaction. And what that means is that these are reactions that go one direction. They just go and make products. Now, you might say, well, don't all reactions end up making products? Well, they do. However, there are some reactions where once they make products, the products can go back and make reactants again. And this is all based on that idea that collisions is what's causing a reaction to occur. So if your reactants can collide or hit one another and make products, then in theory, the products can also collide with one another and convert back to reactants. And in fact, that's what we see with many reactions, and these are what we call reversible reactions. We can actually see reversible reaction in action fairly easily. We can let a reaction go for some amount of time, and at some point some of those reactants will convert and make products, but after a certain concentration of products is reached, then you don't see any more products. And the reason for that is because the products are going back and making reactants. So even though you still have some reactants left, those reactants go and make product, but then the products go back and make the reactants again. So there is this situation where the rates of the formation of product is equal to the rates of the formation of the reactants. That particular point is what we refer to as a chemical equilibrium. And this is really the point when we consider that a reversible reaction is finished, meaning that it's complete. So that's unlike an irreversible reaction where the reaction is considered complete when you've consumed all the reactants. In a reversible reaction, the reactants are never completely consumed. However, they would be considered complete when they've reached chemical equilibrium. Here's an analogy to chemical equilibrium. Let's say at the beginning you have a lot of people on one side, which is Narnia in this case, and some of those people start crossing over to the other side, which is Middle Earth. You can consider this to be your reactant, that to be your product. So at the beginning of reaction, there's a lot of reactants, very few products. As the reaction progresses, you would have more people crossing over this side, right? So eventually, some of those people on Middle Earth is going to start to cross back. However, there's some people from Narnia who is still going to cross over to Middle Earth. And at some point, the rate of migration, in this case of going from one to the other and vice versa, are going to be equal to each other. And that's when we reach chemical equilibrium. And that's the same exact thing with reactions. So the question is, how do we know that a reaction has reached equilibrium? So I said that earlier, that you can measure the concentration, and if the rates are equal, then we know if we've reached equilibrium, because over time, the way we tell that a reaction has reached equilibrium is that the quantity of the product and the reactants don't change. This is illustrated by this plot right here, time on the x-axis. So at the beginning of a reaction, time is equal to 0. I have a lot of reactants, and I don't have any product. This axis here is the concentration of each of those species. As the reaction progresses, I would use up my reactants, so slowly the concentration of reactants are coming down, and the concentration of product is going up because I'm making those products. Now at some point, the products and the reactants quantities, their concentrations no longer change. And at that point, I know I've reached equilibrium. And again, why don't they change? It's not because nothing is happening. Actually, a bunch of things are happening, but the rate of the reactants making product is exactly equal to the rate of the products reconverting back to reactants. So we can find out that a reaction reaches equilibrium if we can measure that the concentration of reactants reactants and products don't change over time. So that's one way we can tell. Another way is we can calculate a special ratio that is called the equilibrium constant, which has a symbol uppercase K, or sometimes written as KC. If your reaction looks like this, with the lowercase letters representing the coefficients and then the uppercase letters representing the species, then the equilibrium constant expression is going to be the concentration of each of these species, first with the products on the numerator, raised to the power of its coefficient, divided by the reactants, each of which is raised with the power of the coefficient. Now, these are equilibrium concentrations, and when that number is calculated, we'll find out what the ratio of products and reactants is at equilibrium. So if, for example, this is a reaction where it makes a lot of products, then this number will be a big number. If this is a reaction where very little of the reactants make product, then this number will be a small number. So let's take a look at an example of how to solve for the equilibrium constant for a given reaction. So this question says, what's the K value for the reaction 2N2O5 goes to 4NO2 plus O2 if the equilibrium concentrations of the species are given as written? So the first thing is always to write what we call the K expression, which is just how the mathematical expression of the equilibrium constant is written for that particular reaction. And remember that the equilibrium constant is going to be the ratio of products over reactants. So we would first write the products concentration and then over the reactant concentration. Now, the second part is the stoichiometric coefficient. Each concentration is raised to the power of its stoichiometric coefficient. So NO2 has a coefficient of 4, so it's going to be raised to the power of 4. Oxygen has a coefficient of 1, so it's just 1. And N2O5 is a square. Once we have that, then it's just a matter of substituting in the values of the equilibrium concentration of each of the species. So that would be 0.01 to the power of 4, and then O2 is 0.02, and N2O5 is 0.002, and that's squared. And really what, at this point, you just go ahead and calculate it and find the answer, and the answer should be 5 times 10 to the minus 5. Now, one of the things that's important about the K value is that it's given as a unitless quantity.